basic introduction to VSim, VSim Composer, which is the graphical user interface around our computational code Vorpal. And I'll touch briefly upon using the Hall thruster as an example for a simulation, but we won't really be diving into the actual simulation results of it too much. I'm going to use it more as an example for setting up a problem. So bearing that in mind, the quick outline of what this talk is going to cover, if the slide will go forward, thank you. Talk first a little bit about simulation requirements. And what I mean by that is before you begin to set up a computational or numerical simulation, what kind of core concepts are useful to explore and kind of see just ahead of time? Is it, is the simulation computationally feasible? Following that, I'll walk through a couple of useful simulation concepts for FDTD codes, which is what VSim is. It is a finite difference time domain code. I'll walk through then the VSim Composer simulation setup tab, essentially all of the options available to users there in the visual. If we have time, I will briefly go through simulating the Hall thruster and possibly visualize some of the results at the end of it, and then conclusions and questions. So in approaching a numerical simulation, the first thing that end user really needs to ask themselves is, what is the core physics that they actually want to explore or look at? And this can be elucidated in a couple of different ways. The first is by determining what are the largest and smallest length scales involved in the problem in question. If there is a plasma in this problem, what is the associated plasma frequency for electrons or ions or whatever it is exactly that you're looking to follow? If you have collisions, there's a number of resolution issues there with your particles and collisions. What are the collision frequencies? What are the velocity distributions of them? Are you looking to resolve electron motion or ion motion? Because that will dictate whether you really want to use a kinetic plasma physics code, or if it might be easier / better for you computationally to use a fluid code if you're looking to maybe go after ion motion. Or if you're looking to get both, given Tom Jenkins' talk yesterday afternoon, VSim does now have speed-limited particle in cell, and so it can at least do a rudimentary version of looking at both electron and ion motion. Another way of asking that question is, what timescales are you interested in? Now, all of these are really to get at, what do these requirements mean for the size of your cells, the number of cells that are required to simulate the entire domain, the size of your time steps and the number of time steps in order to then simulate the total of the temporal domain, in order to be able to accurately capture, again, the core physics that you're looking to try to explore. And the number of cells and the number of time steps is typically a good indicator for, is the simulation computationally feasible? If you have 10 billion cells and you're looking to run it on one core, it's probably not computationally feasible. If you have 10 billion cells and you have 10,000 cores, that's a different question. So from these sort of initial questions of just approaching the simulation, what are some concepts that are probably useful to know when we get into FDTD codes? The first one I would say is knowing what a grid is and the guard cells associated with it. So the grids are structured, coordinate aligned, and this just means that the grid lines are along the coordinate directions. Within VSim, one can choose either a uniform spacing or a non-uniform spacing, as is shown, and the coordinates may be either Cartesian or cylindrical. There is a slight caveat on that. For cylindrical coordinates, the 2D grid, it must be a uniform grid currently. We are working on getting it so that cylindrical can also be non-uniform, but that is a work in progress. And this is actually shown in the image on the right. If you notice, in between cells 2 and 3, the X direction is actually larger than the initial two cells, so it can be non-uniform in Cartesian. Finally, the other portion to this slide is the guard cells. And guard cells are actually just sort of additional cells which have to be added just outside of the simulation grid. And these are necessary for being able to have sufficient field values for the simulation region, whether this be for particle boundary conditions, for fields, or for parallel communication if you are looking to use more than one core. A good example of this is the case where a field must be known at each of the nodes of the simulation, so each one of these vertices. In that case, the last node in any direction is going to be owned by the cell that is one beyond the simulation grid, that, nx comma 0, for instance, there. And so then the cells that are one beyond the physical grid must also be included in the simulation in order for the appropriate information to be available for the physical grid. So now that we have a grid and we have the idea of guard cells, we're going to get a little bit into parallelism and decomposition. So decomposition is basically how we break down the grid in order to pass off sub-portions of this one large grid to individual CPUs. So the image that I have on the right here is that same uniform grid, but it has now been broken down into several different sized subgrids via those red lines. So each of these individual subdomains has been given a unique index, 0 through 3 for the 4 different ones. And what I really want to bring attention to is we're going to look at domain number 2 and the green rectangle that extends around it within the simulation region. We'll note that it extends one cell beyond the red lines for domain 2. And the reason for this is that the fields in this overlap region, in each of those cells, the field in that cell is computed by the subdomain which controls that cell. So in the case of the uppermost right corner of the green box, that cell is in domain 3. That field gets computed by domain 3, but the information of that field must be communicated to domain 2 because the cell just below the one that I've been referring to, ny minus 2, nx minus 1, that field information is relevant to the field solve for the cells in domain 2. And so this creates a communication condition for as many additional CPU tasks that you want to create. You're going to create additional overhead because these cells are going to have to communicate back and forth with each other. And so really this is an indicator for people that are maybe new to parallel computing. If you have a domain that's only 100 cells, you might actually end up slowing down your simulation if you split that across 32 cores instead of running it across just 2 or 3 or 5 or 6, some smaller number. So the key here is you can in fact create more work for your computer if you break up your subdomains to be too small. Okay, that'll actually slow down your simulation run. Don't think there's really anything else I would like to talk about as far as the decomposition and parallelism. So we'll go on to one other concept that is worth covering, and that is resolution for collisions. So I talked briefly about making sure that we had spatial resolution and temporal resolution as far as our time step and cell size is concerned. There's also additional resolution questions when we bring particles into our simulations. So there's spatial resolution for the particles, and that is essentially just making sure that we have enough macro particles in the simulation to be smoothly resolved across all cells. So for instance, again, if we have 100 cells in our simulation and we only have 10 macro particles, that's an issue of spatial resolution. That's one particle per 10 cells. We're not really getting any useful information out of it. For temporal resolution, each interaction, Monte Carlo interaction, is going to have an intrinsic timescale set by the physics of that interaction itself, whether it be elastic or impact ionization. And the probability of that interaction occurring in a single time step can be given by probability goes like dt, the size of your time step, divided by ti, the intrinsic time scale. The fundamental probability for an interaction event to occur is given on the right-hand side there. That's just two macroparticles, N1, N2, a given cell volume V, and the cross-section and velocities of the two interacting particles, sigma V and V. Do just a quick little bit of math, and we can actually get a algebraic answer for what our intrinsic timescale is. This then gives us a condition on how large our time step can be. Our simulation time step dt must be smaller than this intrinsic timescale in order to resolve that sort of natural interaction timescale. Along with spatial and temporal resolution, there's actually one more resolution issue for collisions. And that comes from the need to accurately sample the velocity distributions of the interacting particles. Since the probability for an interaction event to occur non-trivially depends upon the velocity of the particle, right? That's sigma of v and vdt. And since a single macroparticle samples only one point in the velocity space, accurate statistics for particles may only be achieved in some simulations if you have enough macroparticles per cell such that the velocity distributions of the participating species are well sampled within each cell. So there's three sort of resolution issues when it comes to particles and collisions. So with all of these simulation concepts kind of covered here, let's talk very briefly about some of the characteristics of an SPT100 or Hall thruster. In the case of a Hall thruster, the smallest characteristic length scale is typically the Debye length. That's the electron shielding radius in essence. In high electron density locations, this could be of order a few tenths of microns, so something like 10 to the minus 7 meters. And that's going to dictate essentially how small our simulation cells need to be in order to resolve the physics around the sheath. Well, longest characteristic length of a Hall thruster is basically the size of the device. For an SPT100, those are roughly a few centimeters, maybe 5. And finally, then for temporal, the electron plasma frequency is a few gigahertz, and that then would place a constraint on how large or really how small a time step we can take. So we're looking at stuff that's of a nanosecond or smaller, honestly, if we want to get better resolution. So again, using the Hall thruster just sort of as the example to walk through what VSim Composer is and all the options available to it. VSim Composer is the graphical user interface that we have wrapped around our actual computation engine, Vorpal. When you first open VSim and open an example, say from new from example, this is what you would be presented with. The blue box on the left is the elements tree for your simulation. It contains basically everything that the end user will have available to them. The lower box, when you select an item, will pop up with the editable attributes, so you can change things around. And then the red outlined box is the three-dimensional view for whatever shape, geometries, grid you have in your simulation. Before I go through a lot of the options in the elements tree, I do want to mention it's currently covered by the two colored borders, but there is a button to switch your view from the 3D view to looking at the built-in materials within VSim. It should be noted that these materials are not immediately included in your simulation. This is just a table of built-in values that you can add to the simulation if you so choose. And I can show how to go through that in a little bit here. Going back over to the elements tree, I'm going to skip the first couple options there, the description of your simulation. That's exactly what it sounds like. And I'll touch upon constants and parameters after, but I want to first go to basic settings because this is really the most important part of the visual setup. This controls the vast majority of the physics that will be contained in your simulation. So the first option there at the top there is the surface meshing tolerance. And this determines the relative size at which small cells from a mesh geometry surface are dropped. Basically, all this is your geometry surface mesh is tied to the grid mesh / resolution. And this is for our proprietary cut cell algorithm. If the geometry meshed cells are smaller than this value for the grid mesh, then VSim will essentially drop it from the surface geometry. So if I have a grid cell size of, say, 10 to the minus 10 meters, and my surface meshing tolerance is 1/2, then anything that is smaller than 1/2 an angstrom is going to be dropped from the geometry surface, and it's just going to be kind of covered over. For any geometries, or sorry, for any simulations that do not contain any geometries, this can just be set to 1 because, again, the surface geometry mesh is tied to the grid mesh / resolution. Following this is the CFL number. For those who don't know, this is the Courant-Friedrichs-Levy condition. And this is basically how large of a time step you can take without violating the condition that a particle does not skip cells. If you have a particle in one cell and it transitions into a neighboring cell, that is all well and good within one time step. If you have it transition past that neighboring cell into the extended neighbor, that can cause a lot of issues numerically, and the CFL number is a way of preventing that from happening. Basically, you just need to pick a value at 1 or less than 1, because for EM simulations, the time step is reduced proportionately to this value. So you always want to have it be less than 1. Following the CFL number, just below it is our time step. Now, if this time step is set to a value that is non-zero, VSim will just use the value that is placed there. We can see, in my case, it's hard-coded, 3.7 by 10 to the minus 13. But this could also simply be placed as a constant or a parameter and allow it to be changed accordingly there. If the time step here is set to 0, then VSim will calculate a reasonable time step for you based on a variety of factors. Following that is just the total number of steps in your simulation. Again, it's hard-coded here, but you can make it be a constant or a parameter and have it be changed accordingly a little bit more easily. Following the number of steps is just the steps between dumps. This is the number of time steps between sequential dumps of data to HDF5 formatted files. Following that is the dimensionality. This is where you're deciding if you want a 1-dimensional, 2-dimensional, or 3-dimensional case. We can do all 3 dimensions in Cartesian. And following that, in cylindrical, we currently only have 2-dimensional electrostatic in the visual setup, but that will be improved upon in the future. Eagle-eyed observers may have noticed that I skipped a couple of things between the dimensionality and the coordinate system. The grid spacing is, as I mentioned earlier, it can be set to be uniform or non-uniform for Cartesian, and for cylindrical, currently it is only uniform. The restored geometries is an option that basically says if you are importing a geometry, a CAD file, a step file, STL, any of those, GDS, as it is imported, there may be small errors, small holes in the mesh of the geometry. VSim will go through and try to heal or close those small holes accordingly if this value is set to true. The MPI decomposition is exactly those red lines that I had mentioned earlier on the decomposition slide. In this case, VSim is going to handle it all under the hood. Especially newer users are not really going to need to mess with this value. Some of our more power users will probably can just get in touch with us to discuss options under the hood for decomposition. The unit length, VSim always operates in MKS units, but if you want to change it from meters to something else like CGS, that option is there, right there. The use GPU, that's always false. VSim will not have GPU capabilities anytime soon. And then verbosity is exactly what any computer user thinks of. It's how much information do you want placed out of this? Okay, so having gone through what I just skipped, the coordinate system, like I said, can be Cartesian or cylindrical. And again, if it's cylindrical, it has to be uniform and two-dimensional. The field solver that can be used determines which equations will be used to calculate the fields. There are a couple of options that show up depending upon which solver you have chosen. I've listed only 2 of our 4 solvers here, electrostatic, electromagnetic. We have a third one, prescribed fields, if you already have a solved external field that is going to evolve in some prescribed manner. We have a solver for that. And then we actually also have one for no fields at all, if you're interested in looking at just the particle dynamics without any kind of field interactions. That said, I'll just briefly touch upon the options that come along with the solvers. For electrostatic, it just asks if you want to have more than the default number of guard cells around your simulation grid again. And for electromagnetic, there are 2 options there for a Cherenkov filter for basically just eliminating noise that comes about numerically. Following our field solver, we have the option to include or not include particles. First option of no particles is exactly what it sounds like, no particles. If we include particles, there are a couple of things that we have to do. In order to help VSim estimate a time step, if we don't give it one, we need to provide VSim with the estimated maximum electron density and the estimated maximum electron temperature. Electron density and temperature is going to help VSim figure out how fast and how many electrons there are moving, which would indicate to VSim how large or small a time step it can take. Along with turning on particles, we then have the choice to turn on collisions. We currently have 4 options for the collisions framework. The first one is having no collisions at all. The second one is our newest, latest, and greatest framework, which is the reactions framework. And that's the one that we've spent a lot of time here for VSim 12 on. As far as including unlimited reactants and unlimited products. Finally, there is our older, prior to the reactions framework, reduced framework. That's our old impact colliders. And then finally, we still have it included just for the sake of legacy, but we also have a Monte Carlo. These are all technically Monte Carlo frameworks, but an old Monte Carlo framework, which is honestly deprecated, but it's there for legacy users. There are 2 final little options here at the bottom of basic settings, being the moving window, which is basically whether or not to use a moving window, which would allow the simulation window to move at the speed of light in the chosen direction. Which would be useful for people that are doing laser pulses or, excuse me, measuring certain portions of the particle beam moving at a velocity close to the speed of light. Okay, I thought there was a question, but mentioning the GPU capabilities possibly. Finally, after the moving window is if we want to include any kind of periodicity. So if you have X periodicity or Y periodicity, you can just pop it in right here, and VSim will pay attention to that. So I went directly to the basic settings because, like I said, this really is where the vast majority of kind of the physics of your simulation is decided upon in the overarching terms. The constants, if Monte Carlo is deprecated, does DSMC still exist? Yes, absolutely. So when I said that Monte Carlo is deprecated, what I meant was we have a particular framework which is listed in VSim as Monte Carlo. Technically, our reactions framework and our impact colliders, these are all Monte Carlo based implementations. So these are all the reactions framework is direct simulation Monte Carlo. So yes, it does still exist. It's maybe more of a wording issue on our part as far as our naming scheme. So I had skipped constants and parameters, so I'll just briefly touch upon them. Under constants, there's a number of built-in constants, the kind of typical ones a user might like: light speed, pi, the elemental charge, the elemental mass. And then the user can add in and define their own constants accordingly. Underneath that is derived parameters. Parameters operate essentially the exact same as constants, except they are, maybe small algebraic changes. So in this case here, theta is pi over 4. The wavelength is, one value times another value, right? Very, very simple kind of manipulations as far as the parameters are concerned. Following parameters, we have the option to create functions, which is slightly separate from spacetime functions, and I'll just discuss both of them here. Within functions, you can create your own or turn on built-in functions. Functions can contain any number of arbitrary arguments, the one thing being that it is preferred they do not include a time function. Otherwise, that would make them a spacetime function. The user supplied expression is a function of the arguments given in the arguments property listed just under description there. And then the expression can include any predefined constants, parameters, or other functions if they've already been defined, as well as real numbers and Python operators. Spacetime functions is essentially just functions, but separated for the end user to hopefully only include functions that involve time there. Following functions and spacetime functions, we have materials. And materials are not immediately included in a simulation when you start it up. There is, as I said, a list of material properties which are included within VSim that can be imported into a simulation, but they are not in the simulation by default. So we can see a variety of material properties: the heat capacity, conductivity, permittivity, etc. And in order to see these predefined materials, we just switch from the 3D view to the materials database. We can also import our own customized materials. So if we have a very specific form of titanium that we want to load in, we just create a text file with the ending suffix of .vmat. And then we just right-click on the materials button, say import materials, and then find that file loaded in. After materials, there are the geometries to which these materials are going to be applied or assigned. And we built a reasonable infrastructure for importing a variety of geometry files. So we can import step, GDS2, STL, VTK, and a couple of the others that are listed there. If for some reason end user would prefer to not use a CAD and wants to design their geometries entirely within VSim, that is also available for them. We have CSG, or constructive solid geometries, a variety of geometries that can be included. And along with that, these CSG primitives can be combined through the sort of standard variety of operations, subtraction, unions, and intersections. I would like to mention again, for use in a simulation, the geometry part must have a material assigned to it. Otherwise, that geometry gets treated like it's made of vacuum, and so it just simply does not exist within the simulation. And so that is kind of key. You can import a material, but you then need to assign that material to a geometry in order for the geometry to show up in the simulation and for it to have the properties of the material that you imported. So there are a couple of steps that users have to kind of be aware of and make sure that they've followed. Following the geometries option is the grid. This is where the end user will actually decide on the total simulation size and the relation of physical coordinates to their cell indices. Grid is exactly what you think it is. It's the grid. If only it was Tron. Finally, following grids, we have our field dynamics. So this is where we set the initial conditions for our electric or magnetic fields if they are in the simulation. We can also add in external fields if there are any. Underneath that is the field boundary conditions. So this is all of the boundary conditions for the simulation. This is where they get applied for fields. And then if there are any current distributions as well. Within the field boundary conditions, one has to do it for all, 2, 4, 6 boundaries. The choice of boundary conditions is listed there from having a launcher to having a perfect electric conductor or magnetic conductor to having matched absorbing layers for damping out any wave signals. Following field boundary conditions and fields are the particles themselves. This option only turns on if in basic settings you turned on particles. Within the particle dynamics and kinetic particles, if you want to add a particle species, as with many of these things, you right-click on it and then choose what exactly it is that you wish to add or what the option is. In the case of VSim, we have neutral particles, charged particles, and electrons. For their emitters, we have secondary emitters, as well as 2 different types of emitters for shape and slab fluxes. For boundary conditions, have them all listed there. There's a variety of them. Typically, it'll be boundary absorb and save, or possibly interior or boundary accumulate, depending upon what exactly it is that you're looking to set up. If you have a particle, say electrons, and you want to load them in, what you would do is choose a particle loader, and that has a variety of settings associated with it, from the relative density to this relative density refers to the maximum electron density when we said that we wanted particles. So 1.0 means load in at that density, and less than that means load in at less. There are a variety of options for the loading. In this case here, it's set to repeat loading. So it'll start loading at the very beginning, and it'll continue to load until the stop time. So basically, this is really being used as a particle emitter in this case here. We can also then define the velocity distribution, as well as the volume from which we want these particles to be emitted or loaded from. Same thing for particle emission. If instead you don't want to load it at the initial start of the simulation or at a specific step or point in the simulation, if you want to have continuous emission, we have shape emitters that can be assigned to geometries within the simulation. Continuing with particles, when you create a particle species, so in this case, electrons here, it will ask for a couple of attributes for that species, including whatever the nominal density of that gas or particle should be, whether or not you want those particles to have variable weights or constant weights, and then of those weight settings, whether they should be computed by VSim or set and specified by the user. Generally speaking, I have found that variable and computed weights tends to work best. Basically, just let VSim figure out what it is that it needs and let it do its thing under the hood. And I already talked briefly about the particle loader, so I will not touch that. Within the histories, this is allowing the user to essentially retain information from every single time step. So I had said previously that in basic settings, the user can specify the number of steps between dumps to the HDF5 file. Now those dumps to HDF5 files contains all of the information of the simulation at that point, and is such that you can restart from those points. But it also only includes the information at that dump time. If the user wants to have all of the information associated from all the steps in between dumps, what they can do is create a history. And this history will then record all the information at every single time step and basically add it into one gigantic log file. So if we add a particle history, we can say, for instance, look at the absorbed particle current. And in essence, what this would be doing is it would say, okay, the electrons have come, I'll set it on my upper X boundary. The electrons come in, they hit it on the upper X boundary, and they get absorbed into that boundary. This history would keep track of every single electron that does that through the entire simulation. And these histories are actually for a variety of items. I know I just used electrons and particles there, but they also hold for fields and a couple other options in there as well, like arrays for particle momentum. One last thing to note is here in the add particle history, you can decide which species you want to keep track of. And there's one other piece, which is macro particles versus physical particles. VSim keeps track of both actually, but it keeps track of the number of macro particles and determines the number of physical particles by the weights of those macro particles. So that is essentially everything in the VSim setup tab. This was everything to do with the .sdf file. Now, there is a couple of things that happens under the hood that I'd like to give end users just a quick, brief glance at so they know something funky is not really happening. And that is, I'm going to do a quick visual to text-based comparison. And what I mean by that is within VSim, we can see here, I have the example of a coaxial cylinder. it says coax.sdf just above the elements tree. And then next to it, it has coax.pre and coax.in. And all that really is the .sdf file is the file that the user interacts with in the visual. If you are a power user and or you want enough rope to hang yourself, you can operate within the .pre file, which is entirely text-based. And so what I'd like to point out here is basically everything that is in the SDF gets converted into the .pre file, and then eventually that gets converted to the Vorpal input file. So just to kind of provide a side-by-side comparison, the description in the SDF matches up with the description in the .pre. Your constants and parameters blocks show up in the same location. You can find a grid block. So everything basically goes from that visual into this macroized text file, and then this eventually gets built into a readable form for Vorpal, our computational engine. Kind of running up against the end bit here of my time. So just very quickly, I'll briefly go through running the simulation. In here, your time step is automatically calculated if it was not provided in the basic settings. If it is, it'll show up as whatever your default input was. Same thing for the number of steps and the dump periodicity. If you want to change your run mode, you switch over to that tab. There are 3 different run modes: serial, parallel, and if you have access to a cluster and you are using the visual, we also have a scheduler. So if you use, say, no machine to pull up VSim in the visual on your Linux supercomputer, you can then use the scheduler to pass off all of your jobs to Slurm. I have a little bit here for analyzing the results. Just very briefly, users can write their own analyzers in addition to simply using the ones that we have built in. In that case, all they need to do is write it in Python, import a public class that we have called VP Analyzer in order to have it show up within our GUI. But it's fairly straightforward to import your own privately built analyzers for your scripts. And finally, in visualizing results, I'm not going to go in depth into this really at all. I'm just going to let people know that there are a variety of options available for data overview, for looking at histories or binning, particle velocities versus positions, phase space, field analysis, and a variety of options there. And with that, I'll just plug what I think the vast majority of people are really looking forward to, and that is the talk by Dr. Daniel Main, using VSim to optimize your magnetron sputtering setup. And that'll be happening in about 15 minutes here. So look forward to that. I know I certainly am. And at this point, I'll leave it open for questions.
Thank you, Dan, for that presentation. Sorry, thank you for that presentation. Very helpful. I know for some of the names that I recognize here, this may have been a little below your skill level, but I know that we have a lot of other people who, when you first log on to VSim, sometimes it just can look very intimidating. We have application engineers. One thing I want to point out is we have resources like this. This presentation will be on our website. We will get the slides up there as well. So the video will be on our YouTube page. The slides will be on our website. If you want to come back to this and use this as a tutorial as you are learning the software yourself. In addition, when users purchase the software, you're not alone. We have people like Dan Murray, like Daniel Main, who you will see here shortly, and you, who you saw yesterday, with his presentation, and their entire job here is to work with clients and help them figure out if they are stuck on a problem and how to set it up, figure out what's the best way, how do you approach it, how do you do it, and how do you make sure that you're getting answers that you can trust. So those guys are here. They are all expertly trained at this point. All three of them have PhDs. And that's their entire job, is to work with you. But in the meantime, we do have resources like this. There is also a learning VSim page on our website as well, which has presentations that we have done in the past and other tutorials, videos, and handouts for you to learn off of. So we did have one question, which is, what is a magnetic conductor and how is it different?
So the magnetic conductor is in the field boundary conditions.
So I know you're not sure on that one, right? On the difference. John, I know that I think I saw you here, or one of my other application engineers. If one of you wants to help us with that question,
Yeah,
that would be great.
Can you hear me?
Yes,
Hello?
we can hear you.
Okay, wonderful. So a perfect electric conductor is something that enforces because that the electric field vanishes within that conductor, and therefore in particular on the surface, which is where we put the boundaries. Similarly, a perfect magnetic conductor enforces that the magnetic field is zero within that, and therefore, as we say, the tangential component must be zero on its surface. So a magnetic conductor is just a perfect analog of the electrical conductor in that it enforces magnetic field has to vanish. So you might ask, well, where the heck do we ever need those things? Well, one place you need those is if you have a very high mu magnetic permeability material, like mu material. And in that case, when you put that in the simulation, then you want the magnetic field. It basically almost acts like a perfect magnetic conductor. There's no perfection in the world, of course. There's no perfect magnetic conductors, no perfect electric conductors, but that is a common approximation that works very well. So that's the answer. I'd be happy to answer any questions. Thanks.
Thanks for that, John. Appreciate it.
If you have additional questions, if you want to type them into the Q&A box there on the bottom, we will go ahead and take them now. Otherwise, our next talk is coming up here in about 10 minutes.
I don't think
so. There is another follow-up question, sorry about that we have, which is, so there is only conductivity applied to different EM field boundary conditions. John?
Okay, I don't see that question. Let me see, where do I find that question? I'm sorry, could you repeat the question? I don't see where it is in the interface here. I'm being silly.
So there is only conductivity applied to different EM field boundary conditions. I think that only applies to the two field boundary conditions of the PEC and PMC, correct?
Yeah, I'm having a hard time parsing that sentence. But if what you're asking is, are those the only kinds of boundary conditions one can have for electromagnetics? The answer is Actually, we have a few more. We have boundary conditions such as, for example, ports, which allow a wave of a given phase velocity to exit a system and have no reflection coming back in for a particular wavelength. And those ports are very efficient for what they do, and they take only one cell to implement. We also have matched absorbing layers, which adiabatically damp the wave as it leaves so that there are no reflections. So you kind of got to figure out what's the best approach to modeling your physical system. If your plasma or whatever it is really inside of some sort of metal can, then you want to have perfectly conducting boundary conditions. Those are your best approach to the metal. But if instead you had some sort of incoming wave coming in through a waveguide, then you might want to launch it with either a port, which would mean that if the wave hits the whatever's inside the cavity or some structure and reflects something, that reflection just cleanly leaves the simulation and doesn't come back into it, and thereby not confusing your answers. Or if you are doing something like a radar cross-section, where we have this nice thing called an RCS box that generates waves in a certain region, and then there's inside of it a scatterer, and that scatterer scatters the waves that go off to infinity. Well, we unfortunately can't simulate infinity in a finite computer. And so what we do is we put these matched absorbing layers out there, and then in all directions, it prevents the waves from coming back in. And then that allows us to measure the electromagnetic radiation at a certain distance outside of this, outside of the thing we're scattering off of. We can measure it there, and we can get things like the differential radar cross-section. That is to say, how much the scattering goes into each direction. And it doesn't get, that calculation does not get confused by the fact that waves could, if you didn't do it right, reflect off the boundaries of the simulation and come back in, which something doesn't happen in the real situation. So probably going on for too long, sorry, but there are a number of ways of putting boundary conditions on, and you have to decide for your physical system which is the best one. And that's why we have people like Dan Murray and Daniel Main and so on and so forth, because they can help you get to there.
Yeah, and I will note that we have 13 different field boundary conditions. So we've got a number to address different situations.
Well, I think we're going to have to either get one more or one less, because 13 being...
Yeah, that's a problem.
But since we're scientists, we don't care about that. So that's good.
Okay. Well, with that, I guess there are no other questions. So it will be Dr. Daniel Main's talk coming up here at 10 a.m. Mountain, looking at using VSim to optimize magnetron sputtering setups.